Hey guys, good evening. My name's Liam Ferguson, and I'm a Tau Beta Pi initiate this year for the fall of 2024 semester. And I'm going to do a little bit of tutoring on some circuit problems and the way that we should go about solving circuits, some techniques, and how you can discover which way and which is the best way to solve a certain circuit. So mainly right now, when you're just dealing with circuits without storage elements and everything like that, like capacitors, inductors, etc., there's two main ways you go about solving a circuit. One is through nodal analysis, and another way is through mesh current. Mesh current essentially is just KVL. It loops within certain parts of the circuit, and KCL is nodal analysis, where you're just looking at the sum of currents going in and out of a node and developing relationships onward from there. If I was just taking a look at the circuit, you can pause the video and see how you go about solving the problem. But right away, I feel like it's clear that there's one method that's probably better than the other in terms of nodal or mesh analysis. So if we were to go about this problem using nodal analysis, we would see that we have a big node up here, all of which is being supplied by positive 10 volts. And then we'd have to look down, see other branches, and we'd have to ground a reference node. And since there's only one power source, it really makes it tough to do nodal analysis here. Especially, another thing we have to worry about is the supernode right here. Supernode is basically a voltage source interconnecting between two branches, and if you discover a supernode within your problem, it does complicate it a bit. So right away, if your teacher's nice and they don't provide that, it's probably a good chance that you should go about solving the circuit a different way, if you can see a different way, and I do here. So just right off the bat, I can tell mesh analysis is probably the way to go about solving this circuit. That's because I can look, there's no super meshes, meaning that there's no current source connecting two meshes together. So I don't have to worry about creating a super mesh equation and moving on from there. And I can see that I have three meshes here, each of which is going to have their own mesh current. So I think that's the way we should go about solving this problem. So I'm going to walk through how I was confused at first when I was learning about mesh current, and we're just going to start from the very beginning. So this is a better circuit to be solved for mesh current. So we have a 4 ohm resistor, 12 ohm resistor, 8 ohm resistor, and 16 ohm resistor, and we're given this current flowing this way within the circuit, and that's given, so we do have to create a reference frame in which this current is flowing, sorry. We know current flows from a higher electric potential to a lower electric potential, and since we're going to be using KVL, or the sum of voltage throughout a mesh being equal to 0, we do have to define polarity within the resistors. So current is flowing from positive to negative, higher electric potential to lower electric potential, so we'll label that here. That's good. We can see that this current is actually intertwined with this dependent voltage source. Basically what that means is this voltage source is directly dependent on the current, which we'll define here. So this is a current controlled voltage source. So we have to find what IA is in order to find out what the voltage is flowing through this dependent source. And as we can see, the problem specifically states that we should be solving for the power supplied by the dependent voltage. As we know, power supplied is P is equal to your voltage times your current. And we don't have either right now. We don't know the voltage being outputted by this element or the current, which we haven't defined yet. We know that we can probably write current being supplied by this dependent source flowing out of the positive end of the voltage source. This is because electrons are going to be on this side of the battery. Their higher electric potential is going to push a electric charge out the negative end of the battery, and usually current flows on the opposite way of which electrons travel, so current's going to be flowing out the positive end of the battery to the negative end. So we can safely say that current most likely is going to flow this way out the source. Moving on, let's just define a few more polarities, which we can assume right now. It doesn't matter, that's why I didn't label them before the problem. So right away, I'm just going to label some polarities in the resistors. I don't know if these are right or not. We can see at the end and switch the current if need be. So since we're using mesh current, we define a single mesh current in each one of the meshes, and I always like to have them go clockwise. So we'll define a single mesh current in each mesh, label them I1, I2, and I3 respectively. And the main goal, the big picture here, is we know that this current here has a direct relationship between the mesh currents in the other meshes. So if we can solve for all three of these mesh currents, we can define relationships for all current throughout the circuit. Mesh current isn't necessarily going to be the actual current flowing through an element. It can at certain times, and I'll explain the relationship in a minute. So let's get starting with this problem. So I don't take too long, but I just wanted to set up a base foundation of understanding how we should set up this circuit before we do anything else. So here we go. We have a pretty good idea of what's going on. So this is the first loop here. So we have to create a mesh equation. And sorry, I'm left-handed, so I'll lift my hand up every second or so you guys can see what I'm writing. So loop 1, we need to define a relationship between the actual current going through, well, the actual voltage, because what we're trying to look for is voltage, the sum of the voltages throughout the entire mesh here. So we know that voltage through Ohm's law is equal to your current times your resistance. And we know we have a 4 ohm resistor here. We don't know the current flowing through it, but we labeled a mesh current value here. And as we can see, as mesh current flows through this resistor, positive to negative, the current flowing through this resistor is actually equal to the mesh current. So voltage is equal to your current times your resistance. First is simply just going to be 4I1. That's going to give you your voltage drop through this resistor. Moving on, we labeled negative polarity, and we always go clockwise. We're following for the sum of the voltages throughout the mesh. Next, we can see that as we go around the circuit, we're hitting the negative end of this resistor. And we know that right here, the current flowing through this is IA. The problem with that is this is the actual current flowing through the resistor, and we have to define a relationship between the actual current and the mesh current values. So we know that in this case, I3 is going to be equal to IA minus I1. Well, IA is going to be equal to I3 minus I1, and the way I usually do it is I just can see that as we were to go around this loop, I3 is equal to IA, and opposite of this is going to be I1 counteracting this current. So we can simply just say that the sum of the actual value of this is just the subtraction, or the subtraction of these two currents. So let's just define a relationship between the actual current and the mesh current values, which is IA is equal to I3 minus I1. Once again, if this was labeled downward, we would do the opposite. It's all about your reference currents that you make, and every problem's a bit different, which is how circuits can get confusing sometimes. So we have our values defined here for IA, and we know that at this point, the voltage is going to be equal to 16 times IA. That's the actual current flowing through it. And now we have a relationship. So it's going to be minus 16 IA, but IA is actually equal to I3 minus I1. And then moving through the circuit again, counterclockwise, we can see that we have minus 8 IA, and we already defined the relationship for IA. So it's going to be minus 8 times I3 minus I1 is equal to 0. And that's our first equation. So solving this down, we could just multiply everything through. I can do that quickly. Plus 16I1 minus 8I3 plus 8I1 is equal to 0. And then we just combine like terms here. So the final first equation is going to be 28I1 minus 24I3 is equal to 0. And that was our KVL at loop 1. So this is our first equation here. So now we'll go on to the second loop, KVL at loop 2. And now we can pretty much do the exact same relationship here. We can see that the current flowing through this circuit we labeled with this polarity is equal to I2 at that point. So the voltage through this is going to be 12 times I2. This time we had minus IA, as we can see, because we have polarity labeled through the source this way. So now, since we're still going clockwise, it's going to be plus 8IA, so we'll do plus 8IA. And once again, we have to define another relationship between the actual current flowing through this resistor and the mesh current values. And we could pretty much do the same exact thing as what we did for IA. So like I said, what I usually like to do is the mesh current flowing with the actual current flowing through the resistor. You can define this relationship as the difference between the actual mesh currents is equal to this current. So that's simply just going to be plus 8 times I2 minus I3. Right? So we have 12I2 plus 8IA plus, and we know what IA is equal to. It's 12I2 plus 8 times I3 minus I1 once again, plus 8I2 minus I3 is equal to 0. Sum of all the currents flowing, the sum of all the voltages in the mesh is going to be equal to 0 according to Kirchhoff's voltage law. So once again, if we just solve this out, 8I3 minus 8I1 plus 8I2 minus 8I3 is equal to 0. Our final equation for this second KVL at loop 2 is going to be negative 8I1 plus 20 I2 is equal to 0. I'll circle these because we need these. So that's our second equation, second KVL equation. Equation 2. So we only have one more mesh left. That's the third mesh equation, so we'll do KVL at loop 3 now. And once again, we have to follow polarity that we defined earlier within the problem and keeping the same relationships as we did before. So we said that IA was equal to I3 minus I1. We have this is equal to I2 minus I3. So instead of actually redefining a new relationship, switching the currents around and stuff like that, just do the minus sign here for in which you're entering the resistor here negatively. So this relationship is just going to be, we'll start at 16. So 16 times positive 16 because we're going into the resistor positively, I3 minus I1 as we defined earlier, plus 10, that's voltage source, so we have to include that, minus, as we go in here, minus 8 times I2 minus I3 is equal to 0. Once again, just quick algebra, making sure that we don't make mistakes in multiplying all of these sources and all of these current values. I believe that's right, 16 minus 16 plus 10 minus, yep. So our final equation for this after we combine like terms is going to be negative 16I1 minus 8I2 plus 24I3 is equal to negative 10, which we move to the other side. Okay. It's a little complicated, but I think everything's going to come full circle. So right now we have three equations, three unknowns. We have no idea what the values of these mesh currents are. So if we think back to linear algebra, or if you guys have taken linear algebra yet, we know that the best way to solve this is an augmented matrix. So I'm not going to do the calculation here. There's a way to do it. I would put it in reduced row echelon form, or you can just use an engineering calculator online to solve. But now we can just use the equations that we found, these mesh equations, and sub in the unknown values we have. So we have 28, and this is I1, I2, I3. So we have 28, I1, no I2, so 0, then negative 24 for I3 is equal to 0. Same thing for this one. We have negative 8 I1, we have 20 I2, no I3, 0, 0. Now we have negative 16 minus 8I2, so minus 8, plus 24, so 24 is equal to negative 10. and that's going to be equal, once you plug this into a calculator, negative 25 over 22, negative 5 over 11, and negative 175 divided by 132. And that's a terrible, that does not work out very nice at all. So if you're solving this by hand, it might take a minute, hoping that you don't make mistakes. And as we know, the solution for an augmented matrix like this is just going to be I1, I2, I3. So I1 is the mesh current through this mesh is equal to negative 25 over 22. And I'll rewrite it in decimal because it makes it a little easier to see. Negative 1.1364 is what this fraction is. I2 is equal to negative 0.4545. I3 is equal to negative 1.3258. So now we have the mesh current flowing throughout the entire circuit. So we can solve for IA now because we know the relationship we defined earlier between I is I3 minus I1. So we'll do that after, but first, since we're really just looking for the power supplied by this dependent voltage source, we know that P is equal to VI, right? So what is the voltage here? Well, the voltage is just simply the voltage within this dependent source. So that's just 8 times IA. So we can just write it a little abstractly here. So 8 times IA. And what's the current? Well, the current being supplied, well, outputted by this current controlled voltage source, we assume that it flows out the positive end of the source itself. And once again, we define relationships between the actual current and the mesh current values. So we know that the actual relationship here is just going to be I1 minus I2. So the actual current outputted by this source is I1 minus I2. And from here, it's simply just filling in values. We know that 8 times IA, which IA, we define this relationship I3 minus I1. I1 minus I2. And we already have every single mesh current value. We already solved it here, so we can just sub these values in right away. So negative 1.3258 minus a negative 1.1364, so plus 1.1364, times I1, which is negative 1.1364, minus I2, or minus a negative I2, which is plus I2, so plus 0.4545. Okay. Simplifying this down even more if you wanted to, this entire value is equal to negative 1.5152 times negative 0.6819. And this entire value, negative times negative, is a positive. We finally get the actual power supplied by our source, which is 1.033 watts supplied. And that's our final answer. So it's a lot of work. I tried to go into as much detail as I could, how to set up the problem when you're not really given anything, because I had problems understanding how polarity could change and stuff depending on which way you view your current. But yeah, this is probably the easiest way to go about solving this problem. Even you might be looking at this thinking that's pretty insane, but that's circuit analysis for you. There's really only a few methods you can use to solve complex, well, this is still a simple circuit, but solve a non-energy storage circuit such as this one. And yeah, that's pretty much it. I hope you guys enjoyed the video as well as the breakdown of everything. If you want to reach out to me, my email is hk5220@wayne.edu. I can answer any more of your questions if you have them on problems that you're struggling with or anything like that. So thank you.